Bienvenidos, Hushamadid, and welcome UMGC learners from the CMIT-455 Section 6380 course for the Spring 2021 semester. This is the CCNP ENCOR version 8 curriculum from the Cisco Networking Academy, and in this video, we're going to be taking another look at creating a site-to-site VPN. However, this time, we're going to build off the current the former configuration where we took a look at doing site-to-site IPsec VPNs. Here, we're going to be doing GRE, or the Generic Routing Encapsulation, over IPsec and using OSPF as our routing protocol. So as a review, remember, the crypto map configuration, which is sometimes referred to as a policy-based IPsec configuration, is really only useful when we're working with a third party who can't support tunnels. Crypto maps were Cisco's original implementation of IPsec site-to-site VPNs. Again, remember, this all goes back to right around 1998 when it was figured that, hey, we need a secure way to communicate between sites. And so the crypto map was really Cisco's first implementation of those site-to-site IPsec VPNs. However, we noticed that there's some limitations there. What if I wanted to run a routing protocol? Well, that takes us to the step we're going to be looking at here, which is using GRE over the IPsec implementation. So let's go ahead, and again, I'll bring up a number of things that we talked about, not as in much detail as we did in our first video where we were working with Packet Tracer Activity 16.2.2, where we had a pure IPsec VPN tunnel, meaning I did not have GRE running over this tunnel. And as a result, we simply ended up looking for that interesting traffic leveraging the crypto map. Well, now I'd like to run a routing protocol. And so we know that OSPF and EIGRP, those use multicast. Now, can they use unicast? They can, but we're interested in that multicast component and using a GRE tunnel. Now, remember, IPsec supports unicast IP. The problem with the routing protocols comes up when we're using multicast. Remember, 224.0.0.5 and 0.0.6. Those are the OSPF well-known multicast addresses. And EIGRP 224.0.0.10. So that's where you run into the trouble when you want to run a routing protocol between the two sites. And specifically, when we're talking about routing protocols that use multicast. So how do we solve that problem? So we're going to take the next logical step and we're going to run OSPF over a GRE tunnel. Because again, remember, generic routing encapsulation, generic, the G. I can do broadcast traffic, I can do multicast traffic, I can do IPv4, I could do IPv6. So that's what we're looking for, specifically that multicast capability that is offered to us with GRE over IPsec. So we get the generic component with GRE to allow the multicast to be encapsulated and to be protected over the IPsec VPN tunnel. Those are the keys. Now, a quick note, someone actually sent me a note saying, hey, you said that if we're doing NAT and IPsec, that we'd have to be doing ESP. Is that actually true? Why wouldn't AH work if we're encapsulating everything in UDP? And so let me segue real quickly here over to RFC 3948. And this is all about the encapsulation of IPsec ESP packets. That's what this covers, right? So when we're talking about NAT-T, NAT traversal, it's all about ESP encapsulation, not authentication header, right? Remember, IPsec is not a protocol in and of itself. It's underneath IPsec where we have the encapsulating security, and they call it payload. I keep saying protocol. The ESP, encapsulating security payload, or authentication header AH. Those are two protocols under the IPsec umbrella. Now, when we come down here, you can see that this all focuses on UDP encapsulated ESP headers. And it's simply that, could you get authentication header to work? Yeah, you probably could get it to work, but it's not implemented. It wasn't covered in this implementation of what we refer to as NAT-T, which is simply UDP encapsulation of the ESP packets. Remember, I mentioned that it's going to be UDP port 4500. So this is a great document to take a look at. And in fact, I think if I say AH, yeah, it's actually covered right here. Because the protection of the outer IP addresses in IPsec AH is inherently incompatible with NAT, IPsec AH was left out of the scope of this protocol specification. And this is assuming that we're, again, using ESP. And so that's why I made that statement. So I'm going to stand by that statement, right? You'd be using ESP. That's where you're going to get NAT-T. You're not going to be using AH. All right, so back to the activity here. We've got the legacy activity where we had things set up, but we're not going to do anything here with Packet Tracer. We're going to step out to Cisco Modeling Labs. That's where we want to be. That's where we're going to have a little bit more freedom to do things. So over here on the left-hand side, I've got PCA, and that sits on the LAN segment here, which is 192.168.10, and the PC is just .10, right? So 192.168.10.10. Over here, PCB is 192.168.20.10. So VLAN 10 on the left-hand side, VLAN 20 on the right-hand side, and you can go ahead and say that the left-hand side is California, the right-hand side is New York, and here's our internet service provider, right? And think of this as a cloud. I've got it set up with a single router. Obviously, you're going to be transiting multiple routers. You could be using different ISPs. But in order to facilitate this conversation, all we need is a single router here. Now, we've got publicly routable IPv4 addresses here. Unlike the previous activity in Packet Tracer, we're simulating what would happen between two offices, so to speak. So we've got a 209.165.10 address here, and it's .10.111, and over here it's .20.222. Again, just to kind of keep it simple. And so it's here where we're going to be setting up GRE over IPsec using OSPF to connect these routers. Remember, IPsec, we are creating a point-to-point IPsec relationship here, and the GRE tunnel, which by default is point-to-point, will work out perfectly. So let's go ahead and walk through the configuration steps that are going to be required. So remember, we're going to be using IKE v1, not phase 1, IKE v1, and we will have phase 1 and phase 2, but most importantly, and you can see the router name here is R1-CA for California. All right, so let's get into global config. So what was the first thing that we needed to do? Well, we needed to configure the ISAKMP policy for phase 1. So I'll say crypto ISAKMP policy 10. Now, remember some of the settings that are in here. And what is phase 1 all about? Phase 1 is the control plane. It's all about protecting that shared secret keying material, because we're going to be using symmetrics algorithms here, so we have to have the same shared secret on both routers. And we'll define what that key is. It's going to be ABC123, not my recommendation for when you go to do this in production. But again, how do we protect the shared secret keying material? Well, it's all about phase 1, right? And you'll hear it referred to as ISAKMP or IKE phase 1. Not to be confused with IKE v1. So again, here is our phase 1 configuration. So our authentication, we're going to do pre-shared key, right? Which we're going to enter in with the command crypto ISAKMP key, and we'll put our key in. we're not going to do anything with the default, right? I'll talk about that when we get to static virtual tunnel interfaces, where you can really shorten your deployment time with SVTIs for a scenario like this, a point-to-point, site-to-site IPsec VPN by using the defaults that exist. So we're going to do encryption, I'm going to do AES, and we're going to max it out at 256. Once we do that, we're going to go ahead and use the Diffie-Hellman group, right? Remember, as a quick review, because this is critical, groups 1, 2, and 5, you should not be using these. You shouldn't have been using these after 2012. 14, 15, and 16, those are only good till 2030. My recommendation, I always go with the higher number. That's typically the best, right? Again, typically the best. So we're going to say group 24, and it's that Diffie-Hellman group that is really protecting the keen shared secret information here. And then the final things that we could do, right? I could do a hash. Remember, CIA, confidentiality, integrity, authentication. The C is our encryption. That's the AES component. The A, I'm sorry, skip the I. The I, integrity, is all about the hashing algorithm. So here's my integrity to make sure things have not been manipulated in transit. So I'm going to say hash SHA 512, right? Again, going with the biggest number because all things being equal, more bits is better, right? More bits is better. And so that takes care of the I component, the authentication component. That's where the IKE comes into play, the Internet Key Exchange Protocol, and it's on that pre-shared key, right, that secure key exchange, and it's the Diffie-Hellman component that gives us that A, the authentication piece. All right, so I could put a lifetime in here, right? So the default is 86,400, 24 hours before we rekey, so let's just cut it in half. And remember, these settings need to match the opposite side, and I don't feel like I stressed that enough in the last video. What we're doing here for the phase 1 settings have to match exactly with the other side. Well, yeah, they've got to match exactly. Let's just go with that. Keep them the same. So I'm going to say 86.4, so half of that would be 43,200. So every 12 hours, we're going to rekey. All right, so one more thing we need to do for our phase 1. So let's define what that secret, super secret key is going to be. So crypto ISAKMP key, ABC123. Again, probably not a good idea. Cisco recommends you've got some numbers in here, uppercase, lowercase, special characters, things like that. Now, most importantly is this address value here. If it's an IPv6 shared key, you'd be using this IPv6 here, but we're using IPv4, so we're going to put the peer address in here. Now, always a best practice when you're doing point-to-point, site-to-site, point-to-point IPsec tunnels is to define the address of the other site. If I was to do quad zeros, there's nothing wrong with that, but that is probably not the most secure approach. Now, if you were talking about dynamic tunneling, right, then that changes the conversation. But here it's a static point-to-point, so I'm going to say 209.165.20.222. That is the publicly routable, reachable over the internet IPv4 address of the New York router, router 2. That is my phase 1. Full stop, phase 1, done. Now we're using IKE version 1 when we're doing all of these things, and this is the ISAKMP IKE phase 1 complete. Remember, IKE uses ISAKMP for the key negotiation, and all ISAKMP is it defines how to build, or the requirements, defines the requirements in building the security association. And IKE uses ISAKMP to make that happen, right? And ISAKMP is the Internet Security Association Key Management Protocol. Yeah, Internet Security Association Key Management Protocol, ISAKMP. It's always a tough one for me to remember. All right, so we've done phase 1 on router 1, so why not jump over and do phase 2 on router 2. So we'll go from user exec to privilege exec into global config, and we'll go a little bit quicker here. So crypto ISAKMP, no, I'm sorry, not key. Crypto ISAKMP policy, we're going to use, and I'll use 20 over here. I think I used 10 on the other side to show you that that is a locally significant value, the policy value. And so then what are we going to do? Well, we'll do these things all in turn. Authentication, I keep misspelling things here. Authentication pre-share. We're going to set the encryption to AES 256. We're going to go ahead and set our Diffie-Hellman group, right? That A in CIA, the authentication, that secret key exchange, we'll be using group 24. We'll use the hash for SHA-512. There's our I for integrity. And again, the encryption was the C to obfuscate this data. And the lifetime value is 43,200. Needs to match if you tweak that. And then let's exit out. And now we'll say crypto ISAKMP key ABC 123, and most importantly, that better match, or else your phase 1 won't come up. And remember, when we talked about phase 1, it's all about the control plane. And when we're talking about IKE v1, it's main mode and aggressive mode. We're going to have main mode by default. That is the most secure mode. That's the mode that you want to use. Remember, there's 6 packets in main mode. The first 4 of those are not secure. They are unencrypted. It's going to be main mode messages 5 and 6. That's where the Diffie-Hellman component comes in. That's where that pre-shared key and the exchanging of certificates, if we were using certificates, that's where that would happen. Messages 5 and 6 in main mode. Again, aggressive mode, you're not going to want to use, especially if you're in a government environment, because as soon as the Nessus scan comes up from your security team, they're going to tell you, turn aggressive mode off. And the reason that they're going to tell you that is because the responder has to authenticate first, and then the IDs are in the open, right? And the IDs being passed in the clear is not a good thing. Sure, going to save you a couple seconds when you use aggressive mode, but at the expense of what? At the expense of security. So you're not going to do it. You're going to use main mode when you're using IKE v1. When you get to IKE v2, we're not talking about main mode and aggressive mode anymore. We're talking about something different, which we'll get to. So, when we're talking about the aggressive mode, doesn't show up in IKE v2. So we're going to set our key, and then the address of the other side is 209.165.10.111. So at this point, phase 1 is complete. Again, this is where you can say we're using IKE v1. We just configured the ISAKMP/IKE phase 1 parameters to protect the keying information. And so now what do we move on to? Well, now we're going to move on to IKE/ISAKMP phase 2. Sometimes you'll hear it referred to as IPsec phase 2, because here's where we're dealing not with the keying material. Remember, the keying material is like we're setting up the contract with a moving company, and we pay them with a check. And on that check, you've got the ABA routing number to your bank account. That's the secret, the secret exchange right there, because now we both have the same key and we shake hands and we agree we've got a contract here in order to move all of your things from one site to another site. And so now we're dealing with the protection and the encryption, the CIA, for the payload, for the data, for your cargo that's going to be using this IPsec tunnel. So now let's dive into that configuration, which again is very straightforward if you can spell crypto correctly. So we're going to say crypto IPsec. And again, that keyword, that's kind of why sometimes you'll hear, oh, it's IPsec phase 2. Because it's here where we're using that keyword, crypto IPsec, instead of crypto ISAKMP. And we're simply creating a transform set. So we'll just call it TFS for transform set. Now, here's where you can get into all kinds of exotic choices with how it is you want to protect this. We're going to stick with ESP AES, and we're going to use 256 bits in the key. There's the encryption algorithm that's going to be used, right? So there's my C. Now remember, with ESP, another advantage over AH is all about encryption. With AH, there is no encryption component. So AH is going to offer me the integrity, making sure things aren't getting, changed en route, but it's not going to obfuscate the data. It's not going to encrypt any of that data. It's not going to protect it like we would want it to be protected. We want it to be hidden, obfuscated, encrypted. So ESP has the huge advantage over AH in encryption, and ESP doesn't even need AH. It can do its own integrity check, its own hashing check. And that's where we're going to come in here. And again, we're going to go big, always take more bits better. So we take SHA-512. I would not use MD5, and I would not use the SHA by itself, right? SHA-1, would not use that. Because again, those are legacy. So we've got our transform set configured here, and that's what we need. Now, something else, again, you know, the videos kind of tend to get better and better as I do it again and again and again. What I forgot to mention in 16.2.2 was I talked about the mode, right? And I said, you've got transport mode, and then you've got tunnel mode, right? And I said tunnel mode is typically for connections point to point, or where you've got security gateway to security gateway, right? Or router to router. That's where we would use tunnel mode. Tunnel mode is the default. Forgot to mention that. Tunnel mode is the default. And typically you're going to be using tunnel mode when you're doing site-to-site IPsec VPNs, because by default, tunnel mode, that's sort of the definition of tunnel mode. Whereas transport mode, one of the differences is it only deals with layer 4 and above. So we want to deal with everything, right? We want to be as secure as we possibly can. So we would say mode tunnel. Mode tunnel is the default, right? So there is our phase 2 configuration. Now remember, we're still going to be dealing with a crypto map. It's not going to look, it looks similar to what we did, but we'll come back to that. So let's come over here to router 1. And let's finish up phase 2 on router 1. So I'm going to say crypto IPsec transform set TFS, and what do we say? AES, I'm sorry, ESP AES, ESP AES 256, and then we're going to go with ESP. What are we talking about? SHA-512 for the integrity, right? And then again, mode is tunnel by default, so we'll say mode tunnel, and that's our default mode, is going to be that tunnel mode. All right, so now that that has been taken care of, the next thing that we're going to do is we're going to go ahead and configure an ACL that's going to identify the generic routing encapsulation as the quote unquote, I'm doing the air quotes here, the interesting traffic, because we're going to create a GRE tunnel. We want all the traffic shoved into the tunnel, and that is what we're going to be encrypting. That's the interesting traffic. That's what we want to encrypt. So let me pop out of here and get back into global config, and let's say IP access list extended, and I'll just call the access list GRE. Now, from here, what is it we're going to do? Well, we want to permit, and remember, all kinds of things that we could permit. IP means you are permitting everything. But that's not what we want in a GRE tunnel. We want to match on and protect GRE traffic going from. Now, learners might get a little confused here and think, oh, well, this will be the GRE tunnel IPs. Remember, we haven't even created the GRE tunnel yet. So it's not the GRE tunnel IPs we use here. It's going to be on the physical interfaces, right? Because ultimately that's going to be the tunnel source and destination, are those two internet-facing, publicly routable IPv4 addressed interfaces on router 1 and on router 2. So I'm going to say from host 209.165.10.111 going, to host 209.165.20.222. Now, it looks similar to the ACL that we configured in this activity here. But remember, over here, we were permitting IP, and we were saying anything from this subnet on the left-hand side, 192.168.1, is allowed to, or should be encrypted and matched when the source IP is 192.168.1 anything in the /24 going to 192.168.3/anything in this /24 over here. That's what we were matching on. That is not what the interesting traffic is for us here. We want to encrypt traffic that's going to be routed in the tunnel, the GRE tunnel, right? And so when you're doing crypto maps and only crypto maps with IPsec, with no tunnels, that's why you'll typically hear policy-based IPsec. That's what that means. When you hear policy-based IPsec crypto maps, that means you don't have tunnels. And interestingly enough, when you are using GRE tunnels and IPsec and GRE over IPsec, you hear that referred to as routing-based IPsec, because you're typically running a routing protocol over that GRE tunnel. That's typically why you're using the GRE tunnel and not sort of the legacy crypto map policy-based IPsec, right? But again, remember, the use case for crypto maps is really if you've got like some third party that doesn't support tunnels, like they don't support tunnels. And if you're Cisco and Cisco on both sides, SVTI, right? That's kind of my teaser for the next videos that are going to be coming up. That static virtual tunnel interface, which is going to get rid of all of this crypto map, all these shenanigans with crypto maps that we're having to deal with. We're not going to be dealing with that anymore when we get to SVTIs. All right. So that is my extended IP access list that basically states, hey, GRE traffic that has a source IP and destination IP of those values, that is what I want to match on. That's what I'm interested in encrypting. And then over here, and this was another point I feel like I may shied away from in the previous video on 16.2.2. These ACLs need to mirror each other. They need to mirror each other exactly. I'm going to say exactly. You want to keep them exactly the same, right? And so I'm going to say IP access list extended. We're going to call it GRE. But here's the part that needs to be identical, right? We need to make sure that we are matching, but mirroring it in reverse. They need to match each other in reverse. So permit GRE host 209.165.20.222. Remember, I'm on router 2, so this is what the sourcing would be. And then going to host 209.165.10.111, right? So they need to mirror each other exactly. And so I said match each other. They need to mirror each other exactly. They don't need to be the same ACL. They need to be the opposite, right? They need to be the mirror of each other. And that's what I'm trying to stress there, right? I felt like I didn't cover that well enough when we had covered 16.2.2. All right, so all of our phase 1 configurations done. All of our phase 2 configurations done. Now we're laying the foundation for what is going to be the crypto map. So let's jump into the crypto map configuration. Again, I'll keep it in sequence here. We'll do router 1 and then we'll swing back and we'll do router 2. So I'm going to say crypto map, and we're going to throw a command in here, which is the local address command. And actually, if I do a question mark, actually, let me put the name of the crypto map first. We'll call it VPN map. So if I do a question mark here, you can see we've got this local address option that we can use. And it's interface to use for local address for this crypto map. And again, it's just another way of identifying myself, the router here. And router 1, it's gig 01. And so it would grab the address off that interface. Now let's dive into the crypto map configuration. So crypto map VPN-map. And this is where we say IPsec ISAKMP, right? Because again, I just didn't go far enough. I was like, wait a second, did I mess something up there? IPsec, sorry, IPsec, crypto map, VPN. Do I have something wrong here? Crypto map, and then the name of the map. Oh, we want to put, I look at the sequence number, got ahead of myself. IPsec, ISAKMP, there we go. So we're just going to use map number 10 as the local number here. I'll use 20 on the other side to show that that's locally significant, the map number. All right, so now we're in the crypto map configuration. So we could put a description like we did in the activity, and I'll, just throw some characters in here. So we did that in the activity. Now, what's really important is what we're going to use as our peer. So we're going to set the peer to be, again, that publicly routable IP address. That's my peer. I've identified myself with that local, excuse me, with the local statement that we used earlier. So I'm going to set the peer. I'm going to set the transform set to TFS because that's our phase 2 configuration. And then, just like the previous activity where we were matching the /24 subnet here, I'm interested in matching that. I need the address in there. The address for, and the address refers to the ACL, right? And again, remember I told you it could be named or numbered. That's why I'm using named here to show you it can be named. And to match the extended ACL GRE. So that takes care of router 1 in California. Let's come over here to router 2. Let's do the same thing. Boy, crypto is a tough word to spell. So crypto map, and we're going to use that local address statement again. And I got to put the name in. I keep forgetting to put the name. VPN map, and we'll say local address 209.165.20.222, right? And again, that's just me forgetting again to put the interface in. So let's do this. I'll just pull this back here. So I just need to drop the interface in instead of the actual address. So we'll say gigabit Ethernet 02 because that's what we're using over here. And then we go into the crypto map VPN dash, whoops, typos galore, VPN dash map, and we have that number, and actually I said I'd use 20 over here, and IPsec ISAKMP. And so what do we need to set in here? Well, we need to set the peer. We could put a comment if we wanted to, 209.165.10.111. We need to set the transform set to TFS. Again, I said you could put a description in here if you want to describe what this crypto map refers to. And then finally, match address GRE, because we named the extended ACL the same thing on both sides. So that takes care of the crypto map. So at this point, the only thing left is for us to apply the crypto map like we did previously in the other activity. So here I would go to interface gigabit Ethernet 01, and I'm going to say crypto map VPN dash map. I'm going to come over here to router 2, just keeping things in order, int gig 02, and we're going to say crypto map. And this time I'm going to get the crypto map on the right remote interface in 16.2.2. I had a challenge there where I picked the wrong serial interface. So crypto map VPN dash map. So IPsec, is it up? Is it running? It is, or it should be. So let's validate, right? So we've created this IPsec Security Association. So what if I say, show crypto ISAKMP, let's check phase 1 SA. Well, there's nothing there because no traffic has been generated to go over this yet. What if I say, show crypto IPsec SA? Do we have an IPsec Security Association? We do, right? But we've got nothing going on. We don't see any activity. In fact, let me go back to the SA and let's do detail, right? And you can see that we don't show that anything's been negotiated yet. So we've got parameters in, but nothing's kicked off yet. With SVTIs, they are always up, right? They're always up. A VTI is always up. Here you can see we're going to need to generate a little bit of traffic to make things happen. But what haven't we done yet? We haven't configured the tunnel interface yet. And remember, up until right here, everything, again, small change in the ACL, we're using GRE instead of IP in that command, but everything, phase 1 configuration, phase 2 configuration, crypto map configuration, application of the crypto map, everything has been the same as what we did in activity 16.2.2. And if we had the ACL set up to simply deal with the subnets, that would be working great right now, but we don't have that. In fact, let's come to PCA and let's say ping 192.168.20.10. Can I ping PCB? And you'll notice that that is not going to work because we're not matching on the traffic from the subnets, from the LAN side. We're matching on things that would be going into the tunnel. That's the important part there. And let's kick a ping off over here, 192.168.10.10. Can I ping PCA? And as you can see, that is not going to happen. So we need the tunnel interface configured. And you might think, again, up until this point, everything we just did was the same as 16.2.2. But now the use case is, well, I'd like to run a routing protocol between California and New York to facilitate, easier scaling with this configuration so that I could add multiple networks in and everything's dynamic using OSPF or EIGRP, whatever the case may be. All right, well, to do that, we take the knowledge that we got from the GRE video and we apply that. So let's go ahead and say interface tunnel 0. And what are the configuration steps that were required for the tunnel? Whoops. So we're going to have a tunnel source, and that's going to be gig 01 on router 1. And then we've got a tunnel destination, which is going to be the publicly routable IP of router 2 in New York. And then we have an IP address that we put on our tunnel. Let's just call this, or let's give it 10.0.0.1 because it's router 1, and we'll make it a /24, right? So we've got our tunnel source, we've got our tunnel destination, and what else did we have? Well, we might want to mess around with the MTU a little bit. And remember, we're using tunnel mode, ESP, AES, right? So what would we do? Well, typically you could shrink it down to 1400. I typically go down to 1360, right? But let's do 1400 here. And because this will bring up a conversation on maximum segment size as well. So we'll say IP MTU 1400, taking into account some of the overhead that we might see, worst case scenario, we're going to be covered with IP MTU 1400. And so if I say do show run interface tunnel 0, we've got our IP, we've got our MTU set, we've got our tunnel source, and we've got our tunnel destination. Remember, it's the IPsec, that extended ACL, that's going to capture any traffic that wants to use the tunnel and encrypt it. It's GRE overlaid on IPsec, right? So let's come over to router 2 and let's set up the same thing. So we'll get into global config. We'll say interface tunnel 0. We'll put the IP on first so I don't forget, 0002/24. And then we'll say, and we'll take care of the IP MTU 1400. And we'll say tunnel source is going to be gigabit Ethernet 02. Tunnel destination is the easy one. That's the publicly routable IP out there on the internet that we're trying to reach. .10.111. And now we've got our, and take a look at that. Tunnel 0 changed to up. Well, let's take a look. Are we sure that we're up? Show IP interface brief. And that tunnel shows up. And if in fact that tunnel is up, I should be able to ping the other side of the tunnel. 10.0.0.1, and there it is. And so let's come over to router 1. And let's get out here. And let me save this config off. We'll do a quick write mem here, just in case. And let's say ping 10.0.0.2. Can I ping the other side? Can I ping that tunnel? I can. But I'm more interested in, is the tunnel, the traffic inside the tunnel, being protected? So let's go ahead and say show crypto ISAKMP SA. Let's look at our phase 1. Let's see what we got going on here. And quiet mode idle. We now have the phase 1 work is complete. The status is active and we are in the quiet mode idle state. The key and material has been exchanged. Everybody is happy. So let's go ahead and say, and I could throw some detail on here as well. And take a look. The detail, great command when you take a look at the detail output. Because what does it show me? It shows me the C in CIA. What are we using for confidentiality? IES is our encryption algorithm. What are we using for our integrity? We're using SHA-512 for the integrity. What are we using for the A, the authentication? We're using the pre-shared key. What Diffie-Hellman group are we using? with that authentication, group 24, here's the lifetime. And I love this, right? Remember, what did we do? We cut the 24-hour window down for the rekey to 12 hours, 43,200 seconds. Is that right? Yeah, 43,200 seconds. So 12 hours, right? So we're good here. Everything looks good, right? We keep alives, I'll leave out of the conversation. We could set keep alives up like we did previously in 16.2.2 when I was doing some demo, but we'll leave it because we're going to have traffic flowing back and forth here with the routing protocol over that GRE tunnel. So phase 1, that's how we take a look at phase 1. That's how we see that things look good. Phase 2, we're going to say show crypto IPsec SA, phase 2. And what should we see? Yeah, I better see, and let's come back up here. Whoops, sorry, up to the top up here. I better see some traffic that's going into that tunnel that's being encrypted, right? Because remember, those pings that I ran were between the tunnel interfaces. So I'm on router 1 here. Let's do this. Let me go ahead and say ping 10.0.0.2, and I'm going to repeat that 1,000 times. And then we'll come over here to router 2, and we'll run that show crypto IPsec SA. And you can see we're at 407. Let me do this. And let's just include in caps, right? That'll be enough. Or actually, I bet you I could get away with caps. So we could see in caps and decaps. And we should get to 1,009 because we just threw 1,000 ping packets through that tunnel and it's being protected, right? Take a look at that. And it stops because, again, there's no more traffic that we're sending back and forth here. So now you're going to think I'm going to click on the PCs. This should be working, right? Well, no. Why is this not working? I've got the tunnel set up. We've got the IPsec set up. Everything is protected GRE over IPsec, but PCA can't ping PCB, and PCB cannot ping PCA. Why might that be? Well, let's take a look at our routing. We'll come to the router 1 California router and say show IP route. Where is my route in the routing table for the 192.168.20 for PCA and router 1? And over here on the New York router, show IP route, where's my route to get to the 192.168.10? Right? So remember, that's my local subnet. 10 is on the other side in California. I don't have a route to get there. So again, 2 ways we can do this, but we want to protect the traffic. We want to shove it into the tunnel. So 2 ways we could do this, just like I showed you in 16.2.2. You could do static routes, right? But static routes are, well, let's be honest, they're static. They're not very fun. How do we make this activity fun? We're going to use OSPF. Why not? That's why we've got that GRE tunnel in the first place, is we want to be able to run a dynamic routing protocol over the GRE point-to-point tunnel. So let's whip up an OSPF configuration here that's going to solve that problem. So I'm going to say router OSPF 1. Again, the process ID in OSPF, that number 1 is locally significant. I'll use 2 on the other side. Here we're going to set our router ID, right? We still want to follow some good practices, and we'll say passive interface default. I'm going to say no passive interface. Now, what interface do you think we're going to say no passive on? Is it the publicly routable IPv4 address interface? No, it's the tunnel interface. So no passive interface, tunnel 0. That's the interface because, again, remember, that interface, tunnel 0, has an IP address. Then it's got a partner, right, on the same subnet on the other side in New York, 10.0.0.1. It's over that we want to run the routing protocol because it's all being encrypted. It's inside the IPsec encryption that we're protecting things. So it's very easy. I need a network statement for my local LAN, 192.168.10.0.0.255. area 0. And then I need a network statement for the tunnel interface. So 10.0.0.1, this is sort of considered a best practice, area 0, to lock it down to the exact IP address. And so now the OSPF configuration on this side is done. On the left-hand side, things are done. PCA still Can't ping PCB. We need the OSPF configuration on the other side. Again, remember, we're kind of faking router 1 and router 2 out to think that they've got a point-to-point connection connecting the two of them. And that point-to-point connection is the tunnel interface. So let's get into global config. Let's go into, wait, to the tunnel already. Sorry, we're going to do router OSPF. And I'll use 2 to show you that that is a locally significant value. We'll say router ID 0002. Remember, the router ID must be different between these two routers. Passive interface default, no passive interface on the tunnel because that's the interface over which we're establishing the OSPF adjacency. Then my network statement, and we'll do some suspenseful stuff here in 192.168.20.0. So we'll take care of the LAN segment network first, and then we'll pull in 10.0.0.2 quad zeros to lock it down exactly to that IP. Area 0. Now, we'll take a look at PCB. Can PCB ping? It can't. It can't yet, but as soon as I hit enter, let me hustle over here and let's wait it out. We're going to have an OSPF adjacency form, and that was what we were waiting for, to go from loading to full. And now when I say show IP route OSPF, and if I spell OSPF correctly here, we'll get that in there. I'm learning the LAN segment network and what is the outgoing interface, over which interface is traffic headed to the 192.168.10.0 going to go to. It's going to go to the tunnel 0 interface, which is being protected by IPsec and that phase 1 and phase 2 configuration that we worked on. And this is the transit traffic. This is the phase 2 that we talk about when we talk about what's the phase 2 encrypting and providing integrity on. This is the traffic going between LAN A and LAN B, or PCA and PCB. It's the data plane that phase 2 is all about. Phase 1 is the control plane. Phase 2 is the data plane, the forwarding plane. So now we'll come over here to PCA, and it's working great. We'll come over here to router 1 in California and say, show crypto, IPsec, SA, ink on caps. And we should see that this number is gonna climb because we're shoving traffic through the tunnel. We're using the encryption. We're using IPsec to do the encryption, and all of our traffic is going into the tunnel. All right, so that is going to do it for this supplemental video. Again, we're going to walk our way up, kind of following the historical path, if you will, talking about crypto maps with just IPsec initially. Then talking about, well, we're going to use crypto maps still, and we're going to use IPsec, but we're going to do GRE over IPsec because now we want to run a routing protocol. We wanted to use OSPF. In the next video, I'll use EIGRP, right? Because again, IPsec by default is unicast IPv4, not multicast. There's no support for multicast, and that's why we turn and do GRE like we're doing right here in order to facilitate this use case. So my lunch hour is up. It's time to get back to work. I hope you enjoyed the video. That's all I've got for this one, and I hope to see you later tonight in the next video.